everybody. I'm Everton de Oliveira, the Professor Agua from the Groundwater Project, and I'm very pleased to bring you another great book of a great author as well. So the book is Darcy's Law in Variable Density Groundwater Systems by FRED MARINELLI. FRED MARINELLI has a PhD in civil engineering from the Colorado State University and over 40 years of experience in groundwater hydrology with a split between university research and private sector consulting, which I deem very good because you have the practical experience that not all professors have. So welcome, Fred. Congrats for your new book. You're a hybrid researcher consulting, which I believe has given you practical common sense to solve problems. Please tell us a little bit about your career and how this book came about, please.
Okay, well, yeah, I have about 40 years experience, a split between doing private sector consulting and with periodic forays into research, but primarily I've been in the private sector. As my career has progressed, I've moved progressively more into mining hydrology. And that's primarily what I've been doing for the last 20 years. Prior to that, like most other people, I was involved in hazardous waste work and Superfund and RECRA. But the last 20 years have been primarily mining hydrology and working at mine sites and almost purely in groundwater hydrology.
Very good. And what about the book? How did you come up with the idea, and why did you write the book then?
Well, I think over the 40 years, I've had maybe 3 or 4 experiences of dealing in systems with high density groundwater. And they were all in the consulting arena. For some of those, I convinced myself that I didn't need to go to the extra complexity of using the pressure form of Darcy's law, but there were several instances where I convinced myself that explicit consideration of variable density groundwater was needed to evaluate the problem. One of those was looking at vertical flow between aquifers adjacent to Great Salt Lake in Utah, okay. Where one aquifer the shallow aquifer had fairly fresh water, but the deeper aquifer had brine water, 200,000 to 300,000 parts per million. And then I had another instance of looking at upward flow, what turned out to be upward flow towards a playa in California at Owens Lake. And again, there were very high salinities for the shallow groundwater. And in both cases, when I dealt with other consultants and suggested that we needed to look at the pressure form of Darcy's law, I sort of got looks of confusion, and I came to realize, and looking back on my own education, that the pressure form was something that you might see the first day of class, and then you immediately go to the more traditional head form, and a lot of people were just not familiar with that there's a more universal form of Darcy's law that is used in other industries, but not so much in groundwater. And I was fortunate when I got my master's at University of Arizona. I had some really good classes from Shlomo Newman, and he went into this stuff. And so it always stuck in my mind. And so when I decided, when I was talking with Eileen Potter about doing one of these mini books, I thought this would be a really cool subject to write about, and it would help me get my arms around it and have, sort of refamiliarize myself with the whole issue. And so that led to what we're calling a mini book which is, it's not meant to be a full-blown textbook, but a book on very specific subject, and with a focus of, how do you do calculations when you are confronted with this type of situation. So
Good. And I think it's very welcome. Well, when we do, I worked with multi-phase flow as well, and had to use the pressure form of Darcy's law, right? And when you go on a day by day, we forget that we use the gauge pressure, right? So we get rid of the atmospheric pressure from the equation. And the other thing is that we assume the density is one period, right? And
oh yeah,
our lives are much easier, right? Much easier. But
oh my, the head form's powerful because it's non-directional.
exactly, it's
You know,
beautiful. It's so
yeah,
easy.
it's very powerful. And fortunately, the vast majority of times when you're doing calculation, the head form is just
good
fine.
enough. It's good enough.
Uh,
Exactly. Exactly.
but
So
I have been surprised by the lack of familiarity of students and
yes,
practitioners,
they don't. Yes, that's
and that, that this more universal form exists. One of my mentors, his comment was that the head form usually works, but the pressure form always works. That's kind of stuck in my head for a long
exactly,
time.
exactly. It's
Yeah.
complete. Yes, you're correct. You're correct. So the density drive flow play tricks on hydrogeologists. Not only rookies, but seasoned ones. They have the same problem because they're so used to the head form of the equation that they don't care. So when should we consider density as an important feature on flow?
Well, if you do scoping type calculations, which is kind of what the purpose of the book was, how to, not to do maybe a simulation of a system, but to do scoping calculations to see if it's important. And it seems to me that it comes into play when you really start getting into significant variations in density, and when the magnitude of groundwater density becomes pretty high.
Yeah.
So when you're getting into the realm of seawater, uh, oil field brines, things that are in the many tens of thousands to 100,000s ppm. And even then, sometimes the head form works okay.
Works. Yes.
But what I recommend is, if you have doubts or concerns, then to do some of these scoping type one-dimensional flow calculations,
Yeah.
and see if they suggest that the density issues need to be considered. And if they do, then you have a more complex analysis to do. If they suggest that it's not going to make a large difference, then you're probably pretty safe using the head form and maybe an average groundwater density. So
Good.
that's kind of the way I look at it. But
That's a good plan.
for systems where density is controlled by salinity, you need to start being in the tens of thousands of milligrams per liter, or ppm. And in temperature systems, would be zones where there's quite elevated temperatures, temperatures in the maybe 50, 60 degrees or more Celsius. And even then, it's got to become, it usually has to be pretty extreme to be significant.
To be significant.
So that's good news. Most of the time,
It is very
most
good
of the
news.
time you can get away with the head form, and your calculations are sufficiently accurate for practical application. But it's good to always keep in the back of your mind that if it's a
I
real
would add,
system.
if you allow me, I would add
Yeah.
sometimes like leach it from from landfills. They might not be on the thousands, but they're very significant, and the density, because it goes as a different, it doesn't mix too much, as you know, in porous media, and it has a significant density to show a difference. And it's not like brine, but it's still, I think it's good to keep in mind when we're far from the source, but grow close to the source, the plume does sink, I believe, right? So we have to be careful.
I would agree with that. I had some instances of looking at leakage from industrial ponds with soil liners, clay soil liners, and the water in these ponds was, quite saline. I thought, well, let me try it both ways. Just look at the heads and use what we're sort of familiar with, and then to do the calculations using the pressure form. And it wasn't earth shaking. It didn't make the flow go in a different direction or triple or quadruple the flux rate. But in some cases it changed the flux rate by 50%. The pressure form, and so it was like, wow, I hadn't even thought of that until I was confronted with a consulting problem, and it was enlightening to work the problem both ways and see what different leakage fluxes you came up with.
I agree with you. I recommend people to keep an eye on it, because it is important. So about you have a thought experiment that you show that drives the whole book, the whole thinking. And from my experience, these thought experiments are very common for astrophysicists, because you cannot prepare or have an experiment, and they're very useful. And I really enjoy your thought experiment, because you have to think before you do, right? You go there and you follow the ring that you presented there, and then things become clear. Tell us a little bit about this experiment, please.
Well, it really came from one of my projects where variable density needed to be considered, and there were some very experienced groundwater people there who didn't agree with me, and it led to a lot of discussion. I kind of devised this thought experiment as a way to show that it wasn't just an issue of trying to modify and manipulate and create new types of hydraulic head that would work with Darcy's law, but that you couldn't come up with any scalar, no matter how you defined it. Even if you defined it as the number of eggs in your refrigerator, you could not define any non-directional scalar quantity that would give the correct flow direction in all parts of a convection cell system. And I got a lot of mileage out of that explanation. And so when I started this book, I thought, oh, I'd really like to present that and then actually solve it with the pressure form.
Yes.
To show that even though it was a thought experiment, it did entail the important aspects of the system, and you could not define any scalar quantity that would always give you the correct direction. The correct direction being in the flow in the direction of a decreasing value of a scalar quantity. So I've had that in my mind for a long time, and so
congrats. It's very good, because it is a great bait, a thinking bait, because we go there and you take a look, and it is provoking, actually, right? Because if you don't go through the equation, you're not going to solve with the head equation alone, period, right?
Yeah. When I was explaining it, I was always talking about potential quantities being a groundwater potential, and the fluid mechanics guys, that sort of didn't resonate with them. And then, one of them spouted out, "Oh, you're talking about rotational flow." And that's when it clicked with the more fluid mechanics guys, because that was their language. My language was potentials. Their language was rotational and irrotational flow. And it ended up we were talking about the same thing, but using a different language. So that was actually kind of fun.
Yeah, exactly. I had that experience when I had a co-supervisor working. He was from oil industry, right? So the language, the lingo is completely different, right?
Yeah.
We're talking about the same thing, but it's in a different jargon. It's not easy to get it. So we have to relearn things. But then it's like you said, it solves all the things because it's more broad. That's the basic. That's very good. So
yeah,
going on this density driven, because we use a different equation, usually it scares hydrogeologists as it is very tough to interpret or to use it. On your book, you showed that a good insight could be obtained from a spreadsheet and a hand calculator. Can you give us some details about that?
well, I've always been a big proponent. I call them scoping calculations, which I do with spreadsheets with a calculator. I use MathCAD quite a bit because it has differential equation solvers.
Yeah.
It is proprietary, so that's a limitation for a lot of people. But I've had some really good mentors during my career, both in the private sector and at the university, and they really honed into me the utility of maybe not using simpler calculations to simulate a complex system, but to give you insight as to what's important. And I've had quite a few experiences where I've done something pretty sophisticated, and then I've taken it to my boss, and he's like, "Well, that can't be right," And then I'd find out I slipped a decimal point, or I didn't consider something important, and so I've really over the years have appreciated being able to do. I don't like to call them simple calculations, but I like to call them scoping calculations that give you maybe 75 or 80% of the answer. And for a lot of consulting,
that's enough
questions, that's all you need. A lot of times those questions have yes or no answers. Is a 10 horsepower pump going to be large enough? Yes or no? And the simple type calculations can answer those questions efficiently. Yeah. And so I do that quite a bit in my consulting work. And over the years, I've left the more complex modeling to younger people who seem to like to do that when they get out of school. So I let them go.
Energetic. And that's true.
So it's not a replacement for numerical simulations or more complex simulations, but it can be very insightful, and a lot of times it can give you all the answer that you really need to answer a consulting question.
And you give examples of situations and mathematical solutions for them, right? So could you tell a little bit how you selected those examples and why?
The examples that I showed in vertical flow, particularly vertical flow in aquatards, come directly from consulting work around Great Salt Lake, and where if one used, in that case incorrectly, the head form of Darcy's law, they got the wrong flow direction. Exactly. And that analysis might say the flow is up, And when you looked at the pressure form, it said, no, the flow is down. And so those come directly from consulting. The convection cell example just was a thought experiment that I needed in order to explain this to certain people so that it kind of resonated with them. Work around industrial ponds and leakage in ponds, again, was most of the motivations for this have been consulting problems, mostly in the mining industry, but not exclusively in mining.
No, oil industry as well. We have lots of leakage of brine from wells and from pipelines, and those are important because we're talking about 100,000 ppm or more, and that is, and people think about the regular flow, the head equation, and that doesn't do it. And it's very common when we have oil fields, onshore, that we see that very common. I've seen.
Well, I had a really cool class when I got my master's degree. It was a class at University of Arizona in well hydraulics. And at that point, I thought I kind of knew a thing or two about well hydraulics because I'd had other classes. And this was actually taught by Shlomo Newman. And what he made us do is we were only allowed to look at petroleum literature.
Oh, okay.
And so the entire class was built around well hydraulics as seen from the perspective of petroleum engineers. And I mean, you would open the book and see an equation and have no idea what it was, and I mean, all these weird symbols and he's going, oh, that's the Tice equation.
The units, because we use, and then we see all the units in pressures in Darcy's and think that were not used in hydrogeology. Yes, true.
That's right. And Dr. Newman would say, oh, that's the Tice equation. And I'd go, really? And it turned out when you did the conversions and did it in terms of pressure, it was the Tice equation. And boy, that was a real eye-opener to see in some areas how much more advanced the petroleum engineering industry was in well hydraulics.
Oh, yes.
And then the outcome of the class was to be able to learn how to translate between the two. And my bookshelf on well hydraulics, probably about a third of that is all books and papers from the petroleum industry. So it was a very eye-opening class to a young hydrologist who thought he knew a thing or two.
For you was an earlier experience. I had that feeling when I was in my PhD, when I had to go through the oil literature, and then everything was different. So we had to get used to all this new, presentation and everything. It is, but like you say, it's eye-opening because you see how advanced it is the oil industry compared to water. Well,
especially with single borehole well hydraulics, because they don't have the luxury of observation wells because they're too expensive. And it's cool to see how it paralleled the literature that I'm more familiar with, the hydrology type literature. So.
When you wrote your book, usually when we write something, we have some reader in mind. What was your target audience when you wrote the book? Who do you think is going to be attract to your book, or who should read your book?
I guess I saw it directed mostly to students and to young practitioners, and maybe not so young practitioners who that I have found are not familiar with this alternate expression for subsurface flow.
True.
And yeah, I think that was the main reason, was to bring
I,
it to the attention of people.
But I still think not only younger practitioners. I think people that are working for a long time, if they take a look at the book, and they might review some of the previous work that they've done, it would be
Sure.
better understood if they had that information in mind, for sure, for sure. So I do recommend for older hydrogeologists that are not familiar to the pressure form of Darcy's law to go through the book. It's very important, very good.
Well, and I think the idea behind this book is that it was meant not to be a full-blown textbook, but something you could pick up and read. And I had originally thought, oh, I'll be able to write this in 20 pages. And it turned out to be more like 50, but it's not in hundreds of pages. It's, you know, it's, we wanted to.
No, it is good. It is good. I think that meet the expectations quite fully. It's very good. Because the other way, like you've done and everybody else has done before your book, you have to go to many types of literature and textbooks of petroleum industry and see if we can get that, but then are not that clear like you put in your book, because you had in mind exactly this audience. So I think it's very welcome, for sure.
Oh, thank you. Yeah. We're hoping, at least I'm hoping, that this might lead to a whole series of these mini books, written by others who, have topics of like this that someone can pick up a book and in not too much time, get some insight into something new and learn how to do calculations. So I'm hoping that this is maybe the first of a series of these mini books that can be of practical use to people.
I do too. I hope many others will come, and they're coming, and you've done a great job. So please make your final considerations. Congratulations again for fine work, and I hope lots of people could profit from the knowledge that you presented to us. Thank you very much.
Well, thank you, and I'd like to solicit the greater community to come up with some more ideas for these mini books, that the Groundwater Project can consider. And if you're a working person, if you're working full-time, it's not like writing an entire textbook. It's a manageable amount of effort for someone to be able to do one of these focus books that's designed to be practical. So I'm hoping that there's interest in the community to do more of these.
I do too. Thank you very much. Everybody, we had here Fred Marinelli. His book, Darcy's Law and Variable Density Groundwater Systems, is a very good book. You should consider take a look, download the book and take a look. It's for free, and I'm pretty sure you're going to learn and you're going to be surprised that you should have used that before. Thank you very much, Fred. Congratulations again for your nice work.
Well, thank you. Very nice to meet you as well.
Thank you very much. Bye.
Okay.